Hello. So I'm working on developing couple courses, both are graduate courses. One is called Rigid Body Dynamics and Control. This is not a first course in dynamics, but it's rather an advanced course. And more than half of the course is going to be control. So the format is, first off, it's video lecture, simulation, and solved examples. Once I set up my own website, it's going to have exercises, etc. But that depends on when I can do that. It's going to be mostly rigid body dynamics, and the references are Spacecraft Dynamics by Kane, and Spacecraft Dynamics and Control, and Advanced Dynamics. So initially, what I'm going to do is we're going to start with rigid body dynamics with a very short selective review of dynamics, not every topic in introductory dynamics, and then moving to rigid body kinematics, and then talking about direction cosine matrix, Euler angles, quaternions, etc. And these are the topics we need for attitude determination. So the application is not just in spacecraft dynamics, it's in rigid body dynamics. So it has applications in biomechanics and robotics. It's the same thing essentially. Then kinetics of rigid body is next. So kinematics and then kinetics of rigid body. And then under kinetics of rigid body, I'm going to talk about, I'm going to cover different subsections, kinetic energy, torque, free motion, etc. And then I'm going to move to nonlinear control. Now here you might think that it's mostly dynamics. It's not. The course is half-half. Then stability, various stability methods, stability analysis methods, and then particularly Lyapunov's methods, and then attitude control implementation. So the course is mostly about spacecraft dynamics and control, but its direct application is, for example, in robotics. All right? And if you have questions, on the first page you have my email address, so you can email me if you have questions. Alright, so the introduction, so let's just cover some basic stuff for now, and that's it. So, and the other thing is I'm trying to make the videos very short. It's going to be like one, and the number of videos is going to be 1 or 2 per, very likely just 1 per week. And it's going to be very short, so it's going to take time, a very long time for me to develop the whole course. And I'm trying to make the videos very short and concise because I have very short attention span. All right. So the first things first. Every parameter we talk about in dynamics is a vector to define, for example, acceleration, velocity, position, angular velocity. These are all vectors, and for that we need a reference frame, and that reference frame is defined using an origin and 3 mutually orthogonal vectors. And then once we have that, for example, for position, for P, you can indicate the position of P in this format, x e1 hat, and e1 hat in my notation is going to indicate the unit vector. So e1 hat, e2 hat, and e3 hats are unit vectors. And then I might also use this notation where I'm indicating e hat r. E hat r is the unit vector along this vector r, and r itself, when there is no under arrow, it indicates the magnitude. R e r hat is the vector and its magnitude and direction. I might also use this notation which shows that my vector is defined in this frame E, or I might show it in this using this notation. X, Y, and Z are the components, the magnitudes of the components of RP, and E1 hat, E2 hat, and E3 hat is my unit vector. All right. So, and then we have velocity and acceleration as discussed in an introductory dynamics course. So one important vector which is less talked about in introductory dynamics is an angular velocity vector. So again, it's a vector. So we need a reference frame. So when I say it's a vector, so note that later talk about how we can set up a matrix that represents angular velocity too. Okay, for now. So angular velocity, if you think about this body as, for example, my rigid body, if I attach a frame to this body, and now I'm using B just to indicate that it's a body attached frame, FB. These are my unit vectors, B1 hat and B2 hat and B3 hat. So I have B1 hat and B2 hat and B3 hat. Then my omega has three components, omega 1 and omega 2 and omega 3 hat. So now just pay attention here that omega itself can be defined with respect to different frames. And if you change your frame, depending how your secondary frame is defined with respect to your initial frame, the components of omega may change. All right? So in this frame, so omega itself is this vector. Right? So this vector, let's say, is defined with respect to another frame, with respect to my initial frame. But then I decide to resolve this vector into this body attached frame and then find the components of this vector in this frame. And once I do that, I can describe omega, angular velocity, in this frame. So if I change the frame, I can compute the components of angular velocity with respect to the other frame. And then this angular velocity vector comes, so we need to frequently use it to describe angular velocity and also to compute the acceleration and velocity in a frame which is, for example, rotating with respect to your initial frame. So it is an important parameter that we need to frequently use in rigid body dynamics. All right, so I've introduced the course. Again, let's just so this is rigid body dynamics and control. Just note that the course is in fact I think more than half of the course is going to be control. So or it's half. So the references are spacecraft dynamics and control, and also this Advanced Dynamics, Greenwood's Advanced Dynamics, but it's mostly these textbooks or reference books. If you have questions, you can email me. And as I said, video lectures, simulations, etc., solved examples. And once I set up my website, I don't know when, it's going to have homeworks and assignments, etc. All right, thanks for paying attention.